Welcome to the second part of an examination of why scientists are so convinced that human actions are driving climate change. My goal here is to explain the underlying science clearly and accurately, avoiding both oversimplification and emotional appeals. This approach contrasts somewhat with certain elements in Al Gore's An Inconvenient Truth, particularly the dramatic animated scene depicting a polar bear seemingly on the verge of drowning due to melting ice. While Gore's film succeeded in raising public awareness about climate change, some of its scientific portrayals were, at times, debatable. This led some viewers to question the overall scientific validity of the message presented. Ultimately, to think like a physicist isn't about solving complex equations. Instead, it's about adopting a mindset rooted in curiosity, critical thinking, and evidence-based reasoning. When addressing big questions, like what causes climate change, it is crucial to rely on reliable data and draw conclusions based on what the evidence strongly suggests, rather than relying on gut feelings or personal biases. Have you ever wondered why we have different seasons throughout the year? It all comes down to Earth's tilt. Our planet isn't sitting straight up and down. Instead, its axis, the imaginary line it spins on, is tilted about 23.5 degrees relative to its path around the sun. This tilt remains nearly constant as Earth makes its yearly orbit. Here's how that tilt creates our seasons. When the northern hemisphere is tilted toward the sun, it receives more direct sunlight. Think of it like shining a flashlight straight onto a surface. The light is concentrated and strong. This makes the sun appear higher in the sky and gives us longer days. All of these factors together bring summer to the northern hemisphere. At the same time, the southern hemisphere is tilted away from the sun, receiving less direct light and experiencing shorter days, which means it's winter there. As Earth continues its orbit, there are times when neither hemisphere is tilted significantly toward or away from the sun. These periods are called equinoxes, and they mark the beginnings of spring and autumn, or fall. During an equinox, both halves of the planet receive roughly equal amounts of sunlight, and day and night are nearly the same length everywhere. These are the transition periods between warm summer and cold winter. Around 6 months after summer, as Earth continues its orbit around the sun, the northern hemisphere begins to tilt away. This causes the sun to appear lower in the sky, and its light strikes at a steeper angle, spreading the heat over a larger area. Additionally, there are fewer hours of daylight. All of these factors combine to make it colder, bringing winter to the northern hemisphere. At the same time, the southern hemisphere is tilted toward the sun, so it is experiencing summer. When we think about seasons, many people assume Earth's distance from the sun is the main reason for hot summers and cold winters. But actually, that's not quite right. While our planet's orbit isn't a perfect circle, the slight change in distance from the sun has only a minor effect on the seasons. The real game changer is the tilt of Earth's axis. This tilt determines which parts of the planet get more direct sunlight throughout the year, causing the seasonal changes. So, when the northern hemisphere is tilted away from the sun, it experiences colder temperatures and winter, while the southern hemisphere, tilted towards the sun, enjoys summer. This same axial tilt, along with other subtle changes in Earth's orbit over thousands of years, is what we call the Milankovitch cycles, and they are what really influence long-term climate shifts, even leading to ice ages. Alright, so the Milankovitch theory is basically this idea that explains huge climate changes over super long periods, like why we have ice ages and warmer periods. It all comes down to how Earth moves around the sun, specifically 3 main things that happen very, very slowly. First, there's eccentricity, which is about how stretched out or circular Earth's orbit is. Imagine Earth's path around the sun like an oval that sometimes gets more squished and sometimes more round, over about 100,000 years. When it's more squished, there's a bigger difference in how much sunlight different parts of Earth get, making seasons more extreme in one hemisphere and milder in the other. Then we have obliquity, or the tilt of Earth's axis. Our planet isn't straight up and down. It's currently tilted at about 23.5 degrees. This tilt actually changes slightly over about 41,000 years, wobbling between 22.1 and 24.5 degrees. A bigger tilt means more intense seasons, hotter summers, colder winters, while a smaller tilt means milder seasons. Interestingly, a smaller tilt can actually help ice sheets grow because cooler summers in the polar regions mean less snow and ice melt away. Finally, there's precession, which is like Earth's axis wobbling like a spinning top, completing a full circle every 26,000 years. This wobble changes when certain seasons happen in relation to Earth's position closest to or farthest from the sun. For example, right now, the northern hemisphere has winter when we're closest to the sun. Precession shifts this timing, which affects how strong the seasons are in each hemisphere over long stretches of time. Physics tells us that ice ages happen when these 3 cycles line up in a way that means the northern hemisphere's high latitudes don't get as much sunlight in the summer. The northern hemisphere is key here because it has big land areas where those massive ice sheets can really expand. Note, in Figure 8.10, the relative peak summer solar intensity at 65 degrees north over 800,000 years shows a decreasing trend at the present time, which implies the Earth should be cooling down. When summer sunlight isn't as strong in the northern parts of the world, due to a mix of Earth's tilt wobble, and orbit, the snow that falls in winter doesn't completely melt. Over thousands of years, this allows snow and ice to build up, eventually forming huge ice sheets. These growing ice sheets actually make things even colder because ice is super reflective, bouncing sunlight back into space. This positive feedback loop then leads to even more ice growth. Plus, changes in carbon dioxide in the air, often connected to how warm the oceans are and what living things are doing, can also crank up or cool down these temperature shifts. You know how the sun's gravity keeps Earth in orbit? While the sun is definitely in charge, Jupiter, our solar system's biggest planet, also plays a significant role. Jupiter's massive gravitational pull subtly tugs on Earth, changing the shape of our orbit over long periods of time, tens to hundreds of thousands of years, to be exact. These small shifts, driven by Jupiter, affect how much sunlight reaches different parts of Earth at different times, influencing long-term climate patterns and even triggering ice ages. This concept is a key part of the Miseducated theory. Imagine you have three random objects floating in space, each pulling on the others with their gravity. Even though they're all moving, there's one special point, called the center of mass, that acts as the balancing point for the whole system. If you were to push the entire group of objects right at that center of mass, the whole system would move in a straight line without spinning. However, if you pushed it anywhere else, it would start to tumble. The interesting part is that, even with all the internal gravitational forces between the objects, the center of mass keeps moving in a straight line at a steady speed unless something from outside the system exerts a force on it. Now, think about trying to balance yourself. Your body, with all its different parts like your head, arms, and legs, also has a center of mass, usually somewhere around your belly button. When you're standing still, your center of mass is directly above your feet, which act as your base of support. Gravity pulls your center of mass downward, but the ground pushes up through your feet, keeping everything stable. But when your center of mass shifts outside, or even just close to the edge of your feet, balancing becomes trickier. Here's why. Gravity still pulls your center of mass downward, but now it creates a rotational force, torque, that tries to tip you over. It's like a seesaw. The farther your center of mass moves from being directly over your feet, the stronger the tipping force becomes. To avoid falling, your body has to quickly move and adjust, engaging muscles to shift your weight and bring your center of mass back over your feet. That's why it's so much harder to balance when you're leaning forward, standing on one leg, or carrying something heavy that throws off your balance. Your body has to work much harder to keep that center of mass aligned. Imagine an ice skater doing a spin. They start with their arms and maybe a leg stretched out, right? When they do that, their body mass is spread out pretty far from the center they're spinning around. But here's the cool part. When they pull their arms and leg in tight to their body, they actually reduce something called their moment of inertia. Think of moment of inertia as how much an object resists spinning faster or slower. Now, there's a physics rule called conservation of angular momentum. Basically, if nothing else is messing with their spin, like friction from the ice, the skater's spinning power stays the same. So, when they reduce their moment of inertia by pulling in their limbs, that spinning power has to go somewhere. To keep it constant, they have to spin faster. It's like their body automatically speeds up to make up for the change. And when they want to slow down, they just stick their arms and legs back out, increasing their moment of inertia again, which makes them spin slower. A simple, analogous spinning physics experiment can illustrate the complex interplay of the Milankovitch cycles. Take a small book and secure it with a rubber band so it won't open when tossed. If you spin it around its shortest side, flipping it end over end, or its longest side, spinning it horizontally, it usually rotates pretty smoothly. However, try tossing it to spin around its middle axis, and you'll notice something strange. It tumbles and flips in an unpredictable way. This oddness of the tumbling book is similar to how the Milankovitch cycles work, though it's not exactly the same kind of instability. It helps illustrate the complex and sometimes unpredictable way three different cycles of Earth's orbit and tilt combine to influence our climate. Eccentricity, orbital shape, the extent to which Earth's orbit around the sun is stretched out or circular, changing roughly every 100,000 years. Obliquity, axial tilt, the angle at which Earth's axis is tilted, varying approximately every 41,000 years. Precession, axial wobble, the slight wobble of Earth's axis, completing a full cycle about every 26,000 years. Just as the book's middle axis creates an unstable tumble where energy shifts unpredictably, the Milankovitch cycles show how these three astronomical factors, each with its own timescale, interact in a non-uniform way. Over thousands of years, they combine to influence Earth's climate, triggering significant variations such as ice ages. Climate models and the butterfly effect. Picture this. You're trying to predict the exact path of 3 billiard balls bouncing around on a table for an hour. It sounds like a total headache, right? That's kind of what it's like trying to model climate change. It's super complex, kind of like a physics puzzle called the three-body problem. It's all about something called sensitive dependence on initial conditions, better known as the butterfly effect. Let me break it down. When you've got just two planets orbiting each other, it's pretty easy to predict their paths. but add a third planet, and suddenly, all three are pulling and pushing on each other in unpredictable ways. There's no one-size-fits-all equation that can tell you exactly where they'll be in the future. Even the tiniest change in where they start can completely change the outcome later on. So, in climate modeling, a small change in things like temperature can lead to wildly different predictions about stuff, like sea level rise decades down the road. But here's the catch. While it's chaotic and unpredictable in the long run, it's still somewhat predictably chaotic. What does that mean? Well, in the short term, scientists can make pretty good predictions. Those tiny differences in the beginning take a while to snowball into huge changes. So, even though we can't predict every single detail of the future climate, we can still understand the bigger picture and get a good sense of what might happen in the near future. And that's why we use superpowered computers to run simulations, making small steps to guess where things will go. But even the tiniest mistake in those steps can get amplified over time, which is why long-term predictions can still vary. When scientists try to determine whether humans are causing climate change, the process is surprisingly similar to a court trial. The entire scientific community acts like the court, gathering vast amounts of evidence. They collect data on everything from current carbon dioxide levels in the atmosphere to ancient air trapped in ice, which reveals historical carbon dioxide concentrations. They also track rising global temperatures, melting glaciers, and higher sea levels. Additionally, they compare today's warming to what Earth's natural cycles, like the Milankovitch cycles, would predict. Based on all this, scientists form a hypothesis, such as, burning fossil fuels is warming the Earth, and make predictions about what we should observe if the hypothesis is correct. Next, their work undergoes a rigorous cross-examination called peer review and replication. Here, other scientists meticulously evaluate the data, methods, and conclusions, searching for errors or alternative explanations. If the evidence withstands this intense scrutiny from thousands of experts over many years, it becomes much more robust. Finally, the scientific community reaches a consensus akin to a verdict. This consensus isn't based on a single study, but on a massive body of consistent evidence pointing to the same conclusion. For climate change, the overwhelming scientific consensus is that human activities are the primary cause of the warming we are observing. It's like having so much undeniable proof that the case is virtually indisputable. The scientific argument for human-caused climate change rests on several key pieces of evidence. Direct measurements of greenhouse gas increases. For decades, global measurements have shown a steady and significant rise in atmospheric concentrations of carbon dioxide and other greenhouse gases since the Industrial Revolution. Historical atmospheric composition from ice cores. Analysis of air trapped in ice cores from Greenland and Antarctica provides a record of past atmospheric conditions. These records show that current greenhouse gas levels are unprecedented in at least the last 800,000 years, with the rapid increase coinciding with industrialization. Milankovitch cycles versus observed trends. Based on Milankovitch cycle data, Earth should currently be very slowly cooling due to a gradual decrease in solar intensity. This directly contradicts the warming trends we are witnessing. Observed warming patterns. The global patterns of warming align closely with what we would expect from increased greenhouse gas concentrations. The bottom line is that both children and adults should be asking questions like, why did the highest point in the Arctic experience rain for the first time? Why were temperatures of 67 degrees Fahrenheit recorded in Alaska during December? Why have more flowers been observed blooming in Antarctica over the past decade? The most plausible explanation for these unusual warming trends is the scientifically measured, ever-increasing concentrations of greenhouse gases, as clearly shown in data such as the Keeling curve. A closing thought, sea level rise is a major and inevitable consequence of these warming trends, primarily driven by two factors, the thermal expansion of seawater and the melting of land-based ice, including glaciers and ice sheets. If these trends continue, coastal areas worldwide will experience flooding, raising urgent questions about how soon and how severe global flooding will become. It is difficult to provide a precise timeline for human-caused climate change to manifest on a biblical scale, largely because biblical-scale events, like the Genesis flood, are described as sudden, widespread, and divinely orchestrated, making direct scientific comparison challenging. Essentially, if current global warming trends persist and greenhouse gas emissions are not significantly reduced, leading to high levels of warming, for example, a peak of 5 degrees Celsius or more above pre-industrial levels, the mean global sea level rise over the next several thousand years could reach 19 to 22 meters, approximately 62 to 72 feet, and potentially as high as 28 to 37 meters, 92 to 121.5 feet. While this may seem far in the future to the average person, in geological terms, it is merely the blink of an eye.